Assalamualaikum, hello and welcome everyone. We are Group 6 from the SMJP 4213, Session 1, Modeling and Simulation course, and today we are thrilled to present our project, the Elevator Control System with PID Feedback. Our team is made up of 4 dedicated members, each with a distinct role to ensure the success of our project. I, Muhammad Iqbal Amran, as the media editor of the project, responsible for crafting, engaging, and visually appealing content to present our work in an impactful way. Working alongside me is Abdul Aqsa bin Abdul Lazim, our project officer, whose role is to monitor progress, manage resources, and ensure that every task aligns with our goals. Leading the overall direction and keeping the team focused is our project manager, Harish Raj anak lelaki Murali, whose coordination and planning are key to maintaining a smooth workflow. Last but not least, our report author, Muhammad Shafiq bin Zulkifli, meticulously documenting each step of our process, analyzing the results, and compiling the final report to showcase our findings and outcomes. An overview of our project. Elevators are essential in modern high-rise buildings, serving as the primary means of vertical transportation for both people and goods. As buildings grow taller and more complex, elevators become an indispensable part of the infrastructure, requiring control systems that are not only safe but also highly efficient and accurate. This project focuses on simulating an elevator control system using a PID feedback mechanism to address this challenge. By incorporating a PID controller, the system aims to improve stability, minimize position errors, and ensure fast response time. The primary goals are to design a precise control system and analyze its response under different operating frequencies. The central problem of our project, modern high-rise buildings require efficient and reliable elevator system to ensure safe and comfortable vertical transportation. However, elevators face dynamic force that can cause oscillations, delays, and inefficiencies. Traditional open-loop control methods are inadequate for managing these complexities, so PID control is used to provide real-time feedback and stabilize motion. The challenge lies in designing a PID controller that ensures fast settling times, minimal overshoot, and minimal steady-state errors while maintaining resilience across various operating conditions, including near resonant frequencies. The objective is to achieve Objective 1 to design a PID system for precise position control. This objective centers on developing a control system that enables the elevator to precisely track the desired position input. Utilizing a PID controller, the system seeks to reduce position error, minimize acceleration, and ensure good clean time. And for the second objective, to analyze the dynamic response of the elevator system by varying the PID parameters and force actuator. This objective aims to evaluate the system performance by adjusting PID control parameters and varying actuator force level. Now we move on to the methodology and result. This model simulates an elevator system where a PID controller regulates the position of mass by generating a force input through an actuator. The reference position sets the desired flow level, while the feedback loop continuously measures the actual position using a position sensor. The actuator force moves the mass against the combined effects of a spring damper, which represent the mechanical suspension and damping of the elevator system. The fixed point anchors the system, ensuring realistic spring damper behavior. This configuration allows the model to mimic the dynamics of an elevator, controlling smooth movement and stopping at precise position, also handling external disturbance. For the initial condition, we set the 5000 as the gain, 0.5 as the time constant of integrator, and 0.1 as the time constant for derivative block. For the stop time, we set to 100 and the number interval is 1000. For plotting graph, we highlight the reference position as the value that we need to achieve, and for the position sensor, we want to monitor the position of the elevator. So, as we observe, at the start time that close to zero, the blue line exhibits significant oscillations, indicating the system tension behavior as it moves towards stability. This oscillation suggests an adjustment phase as the system reacts to initial condition or change. Over time, the oscillations gradually dampen and the blue line converges toward the red line. This indicates the system is stabilizing and tracking the reference position accurately. By reducing the gain and integral and increasing the derivative, further improvement in system stability and performance can be achieved. This tuning approach helps minimize overshoot and oscillation in the elevator's response, resulting in smoother and more precise position tracking with a reduced mechanical stress on the cable. The adjustment ensures a more robust and reliable control strategy for handling dynamic change during operation. As we adjust the PID parameter, the elevator starts at height of 0 meters and quickly move upward toward the reference position. The curve is considered quite smooth with minimal oscillation or overshoot, demonstrating that the system is well controlled and able to stabilize effectively. The green lines provide additional insight into the dynamic of the system, showing that the cable tension starts high during the elevator initial movement. This higher tension reflects the force required to accelerate the elevator and overcome its initial inertia. Once the elevator reaches the target height and becomes stationary, the cable tension decreases and stabilizes at constant value, indicating that the system has reached equilibrium. These two graphs provide a comprehensive understanding of the elevator system behavior. These two views complement each other, demonstrating both the control performance and the mechanical effort required for the elevator operation. To explore the system robustness, the height reference was increased from 4 meters to 6 meters. By maintaining the enhanced PID parameters from the previous tuning, the results confirm that the system performance remains consistent despite the change in the reference height. The elevator effectively tracks the new reference position with minimal oscillation or overshoot, similar to the initial condition. Similar to the previous condition. This demonstrates that the updated PID parameters have achieved an optimal balance, ensuring stability and responsiveness across varying operating conditions. As we observe after previous experiment, so the green lines indicate that the cable tension is reached the peak height to move the elevator up, and once the elevator reaches the desired position, the cable tension is maintained the stability at 60. Together, this analysis demonstrates that the updated PID parameters not only enhance system performance for the initial condition but also extend this benefit to varying operational scenarios. This adaptability underscores the robustness of the tuning approach, ensuring consistent and reliable performance across a range of dynamic requirements. So, to wrap up for our project, this study successfully achieved its objective, demonstrating the effectiveness of a PID control evidence system in precise position tracking with minimal errors, rapid settling time, and reduced oscillation. Through detailed analysis and optimization of dynamic response, including variations in PID parameters and actuator force, the system proved stable and reliable across diverse scenarios. Key metrics such as minimal overshoot, steady state accuracy, and control cable tension highlight the robustness of the design, offering valuable insights to enhance the safety and efficiency of modern elevator system under varying load and conditions. That's all from us. Thank you for watching.